Hello, I'm Tim Maloney, and I'm going to be presenting my slides from the 2024 EOS ESD Symposium. And now let's go to the slide presentation as I share the screen. Okay, the title is Intrinsic Inductance and Time-Dependent Resistance of the FI-CDM Spark. And I have a couple of co-authors here, Payman and Marcos. And let's go straight to the motivation and outline slide. For the last 10 or 11 years, we've had perplexing field-induced charge device model calibration target waveforms to look at, and only some of the small targets fit the simple RLC model as seen over at the right. But we need to understand this as we develop spark-free CDM tests that correlate to our JS002 standard that has an air spark. Understanding of the CDM event in general is critical for understanding those factory handling events that decades ago inspired the CDM test and standard, and also the more recently developed die-to-die assembly events, also a charge device model type of thing. So we're going to fit some waveforms for our small and large targets and a few more out there. And we'll have two approaches toward the waveform fitting and circuit modeling. One is to take the model as shown and make the resistance time dependent. Now that's, we're going to call that the G of T solution, referring to conductance, the reciprocal of a time-dependent resistance. And also, perhaps more successfully, apply just 4 parameters with a 3-pole 1-0 approach. We'll describe what that is, finding that that fits extremely well and approaches a perfect R squared equal 1 type statistical evaluation of the fit. So let's proceed now to this treatment of waveforms fitting a analytic model. We're always faced with what does a good fit mean? For example, if we were to find a good fit to a step response as shown, looking for a solution to the arbitrary function of arbitrary impedance there, it could be explained by an inductance, 0.8 nanohenries in this case, or a time-dependent conductance exponentially approaching a final value. So exactly what happens, there has to be a case for exactly what's going on. And in the case of the inductor here, we would need some phase information to be more sure of it. So we're going to make a case for what these waveform fits mean, and I think we'll have enough inductance to make it pretty convincing, enough evidence to make it pretty convincing. Well, let's look at the problem-solving flow stemming from our work back, and actually goes back to the 2013 symposium, where Nathan, Jack, and I produced a paper explaining a lot of waveforms with 2-pole RLC models, and then that was extended in a 2014 IEEE publication. But what was bothersome was that some of these waveforms did not fit that well, fit the first half cycle best. Of course, that's where we think the destruction occurs, but we had to be satisfied with that for a while. Well, as of 2024, we'll be looking at some G of T fits that follow on some work that was done last year by other authors. But we'll find that those kind of fits are not entirely satisfying, and we'll see why. We'll see better fits and better convergence on a solution with the 3-pole 1-0 approach that we're about to describe. But once we found those fits, I asked my co-authors, months months and months ago, is there a circuit model that has a one-to-one correspondence with these 3-pole 1-0 analytic fits? And eventually, in time for this paper to be submitted, at least, we found a solution. And the circuit model as shown, which was very satisfying, and we'll look at details of that as we go on with this presentation. Well, okay, back to the process from 2013 to 2023, pretty much. We found that the 2-pole RLC waveform sometimes fits, but usually on small targets, as shown at the right. Also, the inductance was never as low as what we predicted from simulations of the probe and fixture. Those kind of estimates always gave lower results. For example, here's a method of moments set of data from our papers in 2021 and 2022, where we found that, yeah, we have a large target, larger than large. This is the field plate itself. And we get quite a good fit with just inductor and capacitor plus artificial resistance, some constant value assumed to apply for the spark, and everything is fine. But that was not the case with real large targets and field plate type targets. This was borne out also with other work that was published at this conference even earlier years, like 2018, for example. So as far as this higher inductance, we got more comfortable about presuming that there is a spark inductance built in from this 2021 paper from China, looking at sparks 10 times bigger than our sparks, grain elevator type agricultural sparks. But that gave us a comfort level with having spark inductance be part of the model for the spark itself. Well, let's look at GUT trials, this variable resistance, before we move on any further. The first thing, okay, we're making the resistance time invariant. And the first thing we did was back calculate what GUT would have to be from the differential equation solution using a waveform. And the first thing I found doing this was back calculation was there's always a GUT ramp, a nice ramp going up for at least a few hundred picoseconds for every waveform we looked at. Now, actually, the ramp solution is also analytic. That would be a Bessel function. But as we found in numerous cases, here's one from last year from paper 1A5. And this is a very small probe, only 0.9 nanohenries, and a small capacitance. So we're going to call this the 1 nanohenry solution. I did a GUT fit to this equivalently to what the authors did with ROT, starting at zero conductance or infinite resistance. And we found, okay, that ramp persists for a while, but then flattens out so that you have the usual damp sinusoid type solution. Okay, that's all good to know, but there's more to be said about GUT. Here we did GUT due diligence here for the small and large targets. As expected for the small target, we're not too far off from a 2-pole solution. And we have a short ramp here, this orange curve down here below, and flattening out to a fairly high resistance of about 22 ohms. Not too hard to get a fairly good R-square type fit. For the large target, it was very hard to get a good fit. This R-square where I quit is not too good. More iteration would be needed. This is a process of fitting an arbitrary function to the waveform. So it's quite tedious with the software platform that we have, which is Microsoft Excel, and doing optimizations through Excel Solver. But yeah, that was not good. And also we have a difficult time deriving any general trends from this. We have small target, short ramp, large target, long ramp, and then in the previous case, a very small target, low inductance and capacitance, and that resistance was lower than the low value for the large target, but much, much lower than the low value for the small target, having similar capacitance. So hard to know what's going on here. We're not too thrilled about this. And as if that was not enough, the GFT or RFT would not be a sole solution to the problem anyway, because we can do a calculation not based on circuit modeling at all, really, just knowing what the external inductor and capacitor are like for the fixture and the probe, do a calculation of field energy versus time from the waveform, and we have a collapse of the field energy as expected, but then a rebound of energy back in the field here at longer times, as you can see. Now that can't happen if we have a pure conductance or resistance as the spark model. We have to have a reactive element, energy storage of some kind, so that energy is stored in the spark at first, as well as being dissipated, and then goes back into the field. So we're giving that a meh as far as our attitude toward GFT, since we have to augment it with a reactance of some kind in any case, and it's not very easy to find a good fit. Well, on the contrary, this 3-pole 1-0 model works quite well for all the waveforms we looked at. We started with the 2-pole aspect. Now this is in frequency domain. This is complex frequency, familiar notation. So the 2-pole model that worked for some targets was augmented by a pole and a zero, an extra pole and a zero, real pole, real zero, make it easy. And that worked quite well. Now I put equivalent notation here for the 2-pole and 3-pole 1-0. The damping factor and omega zero characteristic frequency can be represented in terms of the what I call core RLC values as shown. So everything is equivalent as in the picture. And now a large target that didn't fit very well before is found to be easily fit with this scheme with reasonable core RLC values for the 2-pole element, and then tau 1 and tau 2 substantial values and different values over a nanosecond, and we get a very good fit to the data. Now, in order to do this, to go from frequency domain to time domain with a polynomial ratio like this, we do Heaviside inversion, old technique available in math books, and converted that to the time domain, and then did optimization of the 4 parameters here, the D, the omega zero, and the 2 taus, after determining capacitance from integration of the current. The other thing we did as part of this process was to do some deconvolution on the waveform to remove dissipative effects by the scope and cable. Those effects were all talked about in our 2020 and 2021 papers, and in this year's paper, 2024, we talk about how that was folded into the Excel optimization to make a quick process out of doing the deconvolution and the optimization to fit parameters. So yeah, that all appears in the paper. So, this was reduced to a fairly fast process so we could process a lot of waveforms as shown. Now, the waveforms you've seen in the previous slides are highlighted here. Those are 500 volt small and large waveforms, the small on the left, the large on the right, the Intel waveforms at the top, and thermo waveforms at the bottom. A consistent trend For the small targets is this larger inductance, going up to 6, 7, even 8 nanohenries when we calculate inductance for the probe, and fixture to be 4, 4.5 nanohenries at most. The small target, as we've said, is not too far from a two-pole solution. That means that and certainly what happened was the tau ratio came out pretty high, so that the extra pole and zero almost cancel out. That tau ratio is over 0.9 in many cases. But that's not true for the large target. We really need the tau2 and tau1 to describe the waveform. The ratios are down around 0.5, 0.6. And if you were to try to force the two-pole solution to the large target, you get an R square of about 0.7, which is really pretty lousy. So the 3-pole 1-0 fit is showing to be applicable to all these targets. And it's just not needed as much for the small target, but it does help. And we get our R squares up to almost ideal value. Okay, well, how about when we apply this to the 2023 paper from our esteemed colleagues in Europe? The 1A5 1 nanohenry solution waveform from last year is fit quite easily in a few seconds using optimization plugin from Microsoft Excel Solver. No iterative G of T arbitrary function needs to be plugged in and tried over and over. And we get reasonable values for the core two-pole situation, about 1 nanohenry and 3 picofarads as expected. And R is a good baseline value, but then modulated by the tau1 and tau2, you might say. These taus being down in the 50, 100, 130 picosecond range for an excellent fit. So yeah, this is working out very well to do these fits in the frequency domain, expression inverted to time domain. Well, before we move on, let's look at what that 3-pole 1-0 means. The expression means in terms of partitioning it into a 2-pole expression and then a non-ideal step, because after all, the CDM waveform is a step response to network out there in terms of the current function. Well, if you invert the non-ideal step function only and have that modulating a 2-pole solution, which we know can be realized with the low impedance CCDM type of hardware worked on by myself and Nathan Jack plus others, yeah, you get a non-ideal function like this, main feature being the exponential approach to the final value according to the tau1 parameter, and then the ratio as according to the picture. And so it's a kind of rise time filter, which goes back to when I asked Nathan and others, well, why the rise time filter on the low impedance CCDM? Well, it works better. Okay, this could be why it works better. And in the paper, I discuss how you could realize this kind of filter exactly, but some kind of rise time filter looks like it's called for to stand in for the spark. So we'll move on to further considerations of that pretty soon. But first, let's look at the circuit that corresponds to our 1 nanohenry solution from last year. Our heavily underdamped waveform does have a 3P1Z solution and a circuit to correspond, and here's the circuit. Okay, capacitance as expected, inductance about twice what we are measuring as expected probe inductance. But over in the spark half on the right, we have another capacitor that's kind of a mirror of the fixture capacitance that we know so well. And there's a negative resistance in that outer RLC loop, so that's why the vigorous oscillations, and then those are drained off by the 28 ohms in parallel there, so that it damps out gradually as expected. And all the real poles, all the actual poles and zeros are in the left half plane as expected. So this, this is giving us pause about this, these 3 gigahertz oscillation. Is that something special for the plasma that you have in the arc with that kind of resonant frequency. And also, yeah, the mirroring of the L and C in the spark itself gives an outer loop inductance that's twice as large and a capacitance that's half as large as what's known to be in the external probe and fixture circuit. So it oscillates just about as expected at about the same frequency. And that's what's been fooling us for so long. There's inductance and capacitance built into the spark. Well, that persists then for other CDM targets, quite different target. Here's a large target, 15 picofarads now instead of 3, and a much larger inductance too, because of the 5 millimeter probe and the hardware fixture. So we're seeing 9.6 nanohenries, about twice what we might calculate for that probe and fixture inductance. Again, that larger capacitor is mirrored in the spark itself. And the outer loop has not a negative resistance, but a low resistance of 15, which we're familiar with in trying to model the spark by a single resistor. That's right in the ballpark. So, okay, this pattern of behavior in the spark is holding up for the large target and also for the small target and other examples that we had in our tables there. Here's a minus 500 volt that we, waveform we flipped over so that it looks more familiar. But again, we have about the same inductance as expected from the identical probe and fixture situation, but this smaller capacitance for the small target is now mirrored again in the spark plasma, and we're back to a negative resistance in the outer loop, but with a positive resistance that damps everything out as expected. So these patterns are quite consistent in what we've looked at. And let's put a partition through the middle of this circuit just to make sure you realize that the right half over there is the spark model. Well, speaking of spark models, let's look at them very briefly here in terms of a step response of the derived spark model. Now, that happens to be a 2-pole 1-0 conductance function, but on the top, the small target, that looks like another case of a rise time filter, doesn't it? So some kind of rise time filter for the small target is not hard to imagine being realized. Now, for the large target, the overshoot is huge. So, yeah, a filter to stand in for that is not impossible to realize, even with all positive resistances, but it would be different from the small target. So you can see that it's possible to imagine some kind of filters in a TLP type situation like low impedance CCDM would stand in for the spark, but you won't have a one size fits all situation, but you might have, maybe 2 or 3 sizes could cover the range of device test sizes that we have in mind. That sort of thing certainly would have to be considered, especially if we want to reproduce the JS002 spark in all its aspects. Well, here's a step response for last year's 1 nanohenry solution, paper 1A5. Here the spark itself oscillates in a step response, and that too is possible to realize with actual hardware. The question is, would we have to do it, and is this called for as far as simulation of actual events in the factory? Because in the factory, we have lower inductances, no question of that, lower inductances than our 5 millimeter probe that we've been using for decades. If there's something about plasmas up in the 3 gigahertz range that we should know, let's find out about it, and let's see to what extent our standards need to reflect those real situations in the factory and in die-to-die attach that we're going to have we're going to have to protect against in our testing of devices and CDM situations for clearance, so that they won't suffer any damage in the assembly and in the assembly conditions. Okay, well, let's ask what's going on with the spark plasma. There is a kind of self-matching of the output impedance going on with this mirroring of inductance and capacitance in the spark. Now, we shouldn't be surprised that there is reactive elements in the spark. As we said, we kind of proved that with the field energy calculation. But we know from atomic physics and plasma physics that initiating that plasma is going to create some energy storage as we create ions and excited atoms, and they have nanosecond lifetimes. That's all not a big surprise, and you expect to apply a voltage and see some time delay before you have a current. So current lagging the voltage, that's the definition of an inductor. So the inductance is certainly hard to escape here. Moreover, as we showed with the field collapse calculation, there's a fast transfer of electric and magnetic field energy to the spark. And I speculated about that back in 2014 in that paper, and continue to do so in the present 2024 paper. Something thermodynamic is going on there to cause the spark to self-regulate, to respond to the external conditions and adjust itself to cause some kind of accelerated collapse of the field energy. And yet the physical conditions seem to require reactive elements that return energy to the field. So, there's something having to do with entropy or thermodynamics that is not clear yet, but it's certainly out there and worth thinking about and investigating. Now, moreover, the extra ringing could be due to a plasma conditions under certain conditions of natural frequency. But as I pointed out, a few minutes ago, the R final is what dissipates the stored energy in that ringing. And in terms of time-dependent resistance, those resistors might be time-dependent, but if so, the effect is very subtle because we get a very good R-squared type fit to the waveform without invoking time-dependent resistance at all. So, I have to leave it at that because our goal here was to fit waveforms as well as we can and then make a case for a physical model. This is about the limit of it. And as stated before, the reactance in the spark explains why we can have a return of energy to the field after 1 or 2 nanoseconds. Well, okay, I'm going to say a few things here while we have time about applying all these situations to the idea of a worst case for peak current and even slew rate, amps per nanosecond, for factory CDM events, die-to-die attachment, and so on, where the basic CDM event happens as shown in the picture there, where you have a target approaching the ground plane, and at some distance, little d there, lightning strikes, and there's an event, and yet as we do that approach, the field for constant charge will be constant, and that's Gauss's law. And I'd like to point out that under those circumstances, we have a maximum peak current that can result, and that also presumes a collapse of the damping factor, so that we have a worst case, underdamped solution with a lot of current. But the fact is that the closure distance there, d, cancels out of the expressions. Now, it's certainly having a small d is good in terms of lower total energy, but it's important to note that the peak current reaches a limit based on an LC product an LC product that's a function of the area of the object and the speed of light. Those fundamental limits do apply, and we haven't paid enough attention to that in our white papers, in our committee work on this whole subject. So that's the point I want to make. It's talked about a little more in the paper. You can come up with limits on peak current if you know what the limits on the fields are in the factory. You have a field in terms of volts per centimeter, measurable with a field meter, and then certainly size of object makes a difference. Here's a normalization to a centimeter squared. So you have limits that can be calculated in that way, and we haven't paid enough attention to those limits in our considerations. Moreover, we have a lot of tests where we get a peak current, we get a charge, we get a slew rate that can be tolerated. So that puts a bracket around factory conditions that can be tolerated right there. And we need to capture those values and see if they apply to factory conditions that we might anticipate. That's my point with this. Okay, let's review the problem-solving flow. You've seen most of this before. We started in 2013, 2014 with two-pole RLC fits to a lot of waveforms, but not all waveforms. And yet by 2021, we had a paper that gave us the courage to think about extra inductance in the spark itself with very different sparks, but unmistakable. The G of T fits to our waveforms were not all that satisfying, and we proved through certain measurements that we have to have some kind of reactive element in the spark regardless. But 3-pole 1-0 fits in the frequency and time domain fit very well. And eventually we found a circuit with a 1-to-1 correspondence to that. And the circuit is as shown with the spark on the right, of course, and the caveat that Rx may need to be negative, but everything is well behaved in terms of mathematics because of our final there to bleed off the energy. Finally, let's summarize. The spark plasma changes and adapts to the test fixture or the test conditions for the CDM event. So we have a self-matching of inductance and capacitance that I would find to be the most remarkable property. And it's all captured in a linear circuit with the only time dependence being in the derivative for the inductor and the integral for the capacitor. That's the kind of time dependence we like that can be captured in a simple circuit model, and that appears to apply pretty well. That circuit model could be captured in terms of a TLP filter for spark-free testing. We looked at that a little bit. It's possible to imagine a TLP system as with low impedance CCDM, having a set of filters that stand in for the spark when you have devices of a certain size. We should investigate that possible resonance with plasma at higher frequencies in a case where we have low inductance and perhaps low capacitance as well. There could be something special going on there. And if that happens in real factory conditions, we should think about capturing that in our test standards as well. And that leads into my final observations about how we do CDM testing and can link our measurements a little better with fundamental limits of what can happen in the factory under certain conditions. So with that, we're all pleased with that very much. And this is the point in the conference presentation where I ask for questions, but you can do so even now with that email link. And I might add in finally that there are prospects for capturing this algorithm in standardized waveform evaluation software for CDM. That sort of thing could happen. I'm willing to already have released my code Excel code to developers out there, and others are welcome to use it. That was my intention. My intention is to make this all possible, with the push of a button in a desktop-based application, so you can find out rather quickly from your waveforms what the circuit model is and what's going on out there. This will allow a lot of the physics going on in our CDM events to be understood in greater detail. So at this point, I'll wind this up, and thank you very much for watching. Bye.